Welcome to the 29th video of Quantum Mechanics Done Right, the shortest path from novice to researcher. In this video, we're going to talk about Chapter 23, Single Quanta Measurements. I have an image for you here of a two-slit experiment with polarizers. This is a really cool experiment if it's done with single photons, which just requires using a single photon source and having single photon sensitivity for the detectors. What is nice about it is depending upon what you do, whether you put a vertical polarizer in or a horizontal polarizer in, you can get the light from either slit. But if you put in a 45-degree polarizer, you get interference effects on the light from both slits. And you're allowed to make a change in the choice, and understanding in detail how this works is really important if you want to understand how measurement works. It's a really good example to get into all the details of how single quantum physics experiments work. I should also point out that the polarizers at the slits really do nothing to affect the measurement. So the old argument that you're given that if you watch at the slits, you have to affect the photon by so much that the interference disappears is completely wrong, because we can get the interference back by doing a delayed choice experiment. Chapter 23, Single Quanta Measurements. So in this chapter, I discuss what I think is a true theory of measurement. I am not an experimentalist, so I can't say with full authority that everything I say is 100% correct or even the most important, but I think I get it better than a lot of people do. We talk about the issues that you need in measuring single quanta. First off, you have to have single quantum sensitivity. Second, you have to have a way of amplifying the signal so that it's big enough that it can be measured with a classical device. And you have to be able to do that without reducing or removing your single quantum sensitivity. And then finally, you have to be able to do the detection with the classical device. And those are actually the steps that are most common in a single quantum experiment. We talk about what happens when you look at states that you create that have entanglement, how you can use delayed choice to convert them into product states, and how you can use that to look at situations where you don't have interference or you have interference, and how that works when you think about the different kinds of experiments that you can do. We talk about the role that which way information plays in this. It plays a critical role. It has nothing to do with uncertainty principle. We discuss interaction-free experiments and how they're done with single quanta, and there's a number of interesting things you can do with the interaction-free experiments. We talk about what collapse means, whether you're an ontic or you're someone that believes that the quantum mechanics is a statistical theory and only the probabilities are important, and so only the results of the measurements are what you're predicting. And finally, we talk about the von Neumann paradigm for measurement and what I think is the true measurement problem. And in addition, we get to discuss some really cool single quantum experiments throughout this, mainly in the problems, but there's lots of really cool second quantum revolution experiments that we talk about that we didn't have an opportunity to discuss elsewhere in the book. Hey guys, let's go browse through the chapter. Chapter 23, Real Single Quanta Measurements. This is the one chapter that I took a quote from a physicist. Asher Perez has written a wonderful book in quantum mechanics. I highly recommend you go take a look at that book as well. His quote is, "Quantum mechanical phenomena do not occur in a Hilbert space, they occur in a laboratory." That's a really important thing to remember. When you're busy doing all of this work and you're thinking about all the theory and stuff like that, in the end, what matters is the measurements that you can do. Not how great your theory looks, not how beautiful it is or anything like that, even though we might enjoy that. If it doesn't agree with the experiment, then it's not particularly useful. So we always have to keep that in mind. We are physicists after all, not mathematicians. So we start off with talking about this general strategy for how you measure individual quanta, which really requires us to have single quantum sensitivity. We have to amplify the signal, and we have to be able to then measure the amplified signal on a classical device. A particular example of that is a photomultiplier tube, the Stern-Gerlach experiment, where we're using physical separation, where it gets large enough that we can actually put in different devices to detect the atoms as physically separated. These are all good ways of doing the kinds of measurements, even things like the oil drop experiment, where you use a large oil drop that can have as small as a single extra electron on it to magnify the size of the effect that you're measuring so that you can actually use it visually with your eyes. We talk about some interesting experiments with the Mach-Zehnder interferometer, which is why we have an image of it here. We talk about what is sort of the strategy that you would like to be able to have in order to immediately solve the measurement problem. And we talk about why it can get you quite a far way along the way to solving it, but it doesn't fully solve it. You often have a situation where collapse is really needed to determine what your measurement results will be. And that's the one thing that we don't really have a good theory of, is how collapse works. One of the really interesting experiments that we talk about in the problems is the phenomenon of quantum beats. What you have is, in one kind of a atom that has a ground state and some excited states, you do see quantum beats. In another kind of an atom that has an inverse spectra, where you have one excited state but a larger number of ground states, you don't get beats. Classically, if you do the analysis, you get beats for both. So understanding quantum mechanically why you get beats in one and why you don't in the other is a really important problem to understand if you want to understand how quantum measurement works. We also talk a bit about quantum computation and how quantum computation can really be thought of as using quantum mechanics to prepare a state and then measure it. Then we get into entanglement, product states, and delayed choice. Here we use as an example a Mach-Zehnder interferometer with a polarizing beam splitter, and then putting polarizers either on the paths or putting polarizers before the detectors. There's lots of different options here. It's a complicated experiment to work out. We have all the tools available to us to be able to actually do it. So it's a very nice experiment to analyze. We then talk about in great detail that two-slit experiment with a single photon light source and polarizers over the slits. It's an absolutely beautiful experiment to talk about how measurement works, why uncertainty doesn't play a role when you detect the photons at the different slits, and how the delayed choice works in selecting which of the patterns you get for the probability distribution that you're going to measure. It's really cool how it all fits together in this relatively simple experiment. I should note that there's a beautiful Scientific American article co-authored by Paul Kwiat that also says this is a really good experiment to work with. One of the things I like in particular about it is it works with entangled states, but it has none of this spooky action at a distance, because all of the entanglement is local. And I think it's really cool to separate spooky action in a distance from the effects of entanglement. We then go back and talk about our interaction-free measurements. This also allows us to talk about a phenomenon that is quite popular now called weak measurements. And we talk about what a weak measurement is. Essentially, our interaction-free experiment was doing weak measurements. And we talk about some other experiments that have been out there. In the problems, we talk about some really important experiments, such as atom interferometry. This is like a really important experiment, and you can do incredibly cool things like measuring gravity to a very high accuracy using atom interferometry. We talk about uncertainty, complementarity, and collapse. This is where you have the question that you need to answer for yourself. Am I an ontic believing that the quantum state is real, or am I not an ontic and I believe that quantum mechanics is just a statistical theory, and the only thing that matters are the probabilities it predicts for the measurements that occur at the end? I also dispel this myth of travels like waves but is detected like particles. You won't find too many textbooks that will say that explicitly, although I have found at least one that does that. But you will find tons and tons of YouTube videos who say this is the way in which quantum mechanics works. Spoiler alert, that isn't the way quantum mechanics works. That's not what wave-particle duality is. I think I made that clear in an earlier video. and you shouldn't listen to people that say travels like waves but is detected like particles. And then we get to von Neumann himself. We describe why von Neumann's theory of measurement is not a proper theory of measurement and we shouldn't be listening to it. Really, we shouldn't let a mathematician tell us what the theory of measurement is. We should be listening to experimentalists. That's also a caution to you because I am a theorist. I'm not a mathematician, but I am a theorist. So I might not have the absolute authority on measurement, but I have talked with a number of people about the ideas that I have in this chapter, and at least I don't think I'm very wrong if I am wrong. So in the process of doing this, we do talk about some ideas that people have had in order to do better theories of measurement. One of the ones that I like is the ideas developed by Wiseman. I also like the ideas of Robert Griffiths in his consistent histories approach to quantum mechanics. I must say I don't fully understand exactly what he has done. I would like to understand it better, but he has an interesting approach to figuring out how measurement works. And I think it's something that certainly if you want to work on measurement, you should think carefully about the way that he does things and see whether or not you think it makes sense. We end with a problem that is the problem that Serge Haroche won his Nobel Prize for. It's a quantum non-demolition experiment. It's an absolutely beautiful experiment. We go through and describe it in detail in the problem and have you work through some of the details of exactly how it works. And I think it's just a great way to end the book with such a beautiful and wonderful problem. Now, we still have a number of videos left in this series. I have a video on the epilogue. I have a video on some of the different aspects of things that have been done in the book itself, such as how I made the artwork. I also have a video talking about how we need to separate science from the people who did the science, and a little bit of a philosophical discussion about what that means and how that works and why we need to do that. And so I hope you'll stick with me and look through those additional supplementary videos as well. Hey guys, let's do quantum right.